Last chapter we started talking about two topics. We started talking about position and velocity. We can define position as the idea of where are you? Where are you in space? Like where's Waldo? Where are you? And one way we talk about that is with displacement. Okay, displacement is defined as your final position minus your starting position. So if I give you a racetrack, and let's say it's a 400-meter racetrack, and if we start right here, a runner is going to have zero displacement. They're going to have a displacement of zero because they are going to end where they started. However, if we think about distance, our distance will be equal to 400 meters. Okay, because distance only talks about our length. Distance is like a length. Displacement is where we ended minus where we started. We can define velocity a little bit differently. We can define velocity as the change in position over time. We can go further, and mathematically we can state that as velocity v is equal to delta x divided by delta t. Our delta means our final minus initial, or our start. We can further describe position and velocity using graphs. If I give you a position graph, let's say I'm drawing some lines here, I can tell exactly where I have moved. Right here, this means I have stayed at one place, and let's give that a value. Let's say that's 5. This value there is 5. And let's say this value here is 10. So if I look further at this, I can say, okay, well, right here for this time frame, let's give this some times here. Let's say that's 2 seconds, 3 seconds, 4 seconds. Okay, now here we'll just say 5 seconds. So we have our time frames here. So if I look at just this length here, I know, okay, I have stayed at this position of 5 for 2 seconds. Okay, I look at 2 and I look at 5 and I come across and say, oh, so my position at 2 seconds is 5. Okay, I can also tell how I moved. If I look at the slope of a line, so if I look at the slope, slope is rise over run, I can tell how fast I'm moving because on a position graph, so x, our change in x over time is going to be velocity, like we defined on the previous slide. If I look more closely at that, if I say x, changes in x are up and down movements, okay, because all our x values are on this axis, that's like my rise, then I can say my time, which is my x-axis, I can say, oh, that's like my run. Okay, so my slope is then equal to my velocity. Consequently, I can then look at my slopes, so I can look at my slopes along my different segments, and I can come up with a velocity graph. Since I know that my slope represents velocity, I can put those onto my graph. And how I do this is I say, okay, if I look at my first segment, I have a slope equals 0. Okay, my right here, my slope is equal to 0 because it's a straight line. Because the line is straight, it's flat. That's a good indicator that our slope is 0. So given that, I can say, all right, my velocity is 0. Then all I need to do, so I found my velocity, and I look at my segment, and so I say, okay, my segment went for this long, which is 2 seconds, so I can say I was at 0 for 2 seconds, so that would be like 2. Let me put a little 2 in right here. So that's 2 seconds. I then move to my next segment, and over here I got this segment, and if I look to find the slope, what I'm going to do is I'm going to find my rise over my run. Here, so if I look at my rise I went from 5 to 10, okay? 10 is right here, and 5 is right there, and I did this in 1 to 3, so that's, or 2 to 3, excuse me, so that's 1 second. So I know that I was traveling at 5 meters per second, 5, for 1 second. Let me put that in there. So at second 3, time 3, we moved that at that velocity right there. Okay? Consequently, I can do this again. I look here, okay, that's got a slope of 0, velocity 0, and I did this for 1 second. And then finally, I have a line down here, and that's at negative 10, and that's because we changed from positive 10 to 0, so we were moving towards the axis. All right, we were moving towards the axis, and that means that we have a negative slope value. Okay, in other words, we're moving towards it, so a negative implies direction. So our sign implies direction. Okay, so a negative is towards, positive is away. Okay, so just make note of that. All right. It's important to notice that when I'm looking at my velocities on a position versus time graph, so an x versus t, velocity is slope. Okay, we need a line that's got slope in order to figure out our velocity. On a velocity versus time graph, it's very important to notice we are given velocity on the y-axis. So our height, all right, our distance above or distance below indicates our velocity, how fast we're going. So it's very important to figure out how far we are from 0. That is how we find velocity. There's one final thing we can do with our velocity graphs. So we've talked about how we can create a velocity graph from our position graph by looking at the slope, but we can also go to a position graph by looking at the area under the curve. So area, let me fix my A's, area under the curve. Okay, and this is kind of an abstract concept here. This area under the curve. It's kind of weird, and I guess a question could be, why on God's green earth would we want to look at the area under the curve? Well, this kind of relates to calculus a little bit, so don't let that scare you. Calculus, okay? This relates to calculus, and it relates to a thing called an integral. Integral. Okay, and all an integral is it's just a sum. Think of it as like a sum of little pieces, and there's some fancy things that go along with it, but really all it is a sum, and you guys know how to do sums, I believe you. So when we have an integral, we can figure out what our total distance was. Yeah, so if I look at the area underneath the velocity curve, I put my dotted line in here because I'm done, I can figure out displacement. So area under the curve, it gives me displacement. Let me put a big arrow down here. I like big arrows. Displacement. It gives me displacement. Now to find the actual displacement, what I need to do is I need to find the area, and what's nice about our velocity curves is we've got nice rectangles here. Okay, really easy to find. All I need to do for area for rectangles, I need to know area is equal to base times height, okay, or length times width. I'm going to focus on the first one. That's my favorite version of it. So with base times height, so we need two sides. We need this side and this side. Okay, and it turns out we're given both of them. If we're referring to the previous graph, our times for here were 2 and 3. That's the differences. Okay, so we know one side right here, that's 1. Okay, we know that bottom side is 1. And then we look at our height, and we see, okay, that's our height right there, and that's 5. Okay, so I can look at that. So I know 5 and 1. So if I put those into my equation, I get area is equal to 5 times 1, which is equal to 5. Hey, that's great. We can talk about the units of area, the units there, but I'm going to pass. We know it's displacement, so we know our units are going to be meters. So we have 5 in here. This box right here, that's 5 meters in displacement. All right, awesome. Now don't be deceived. This box does look about the same size as our previous one, but we got to notice what's our difference here. It's 10, and in fact, it's a negative 10. That doesn't work. It's a negative 10. That's important. Our negative sign is very important. We need to hang on to that. So if we look at our distance, again, this went from second 4 to second 5. So we know the difference there is 1. Okay, and it's important to note we always look at the area from the height of the curve, or how far it is away from the axis to the axis. Okay, we always look from the axis or to the axis from our height. Okay, that's very important. We don't go past. We don't go past. No way. We don't go there. Okay, I'm going to just erase that. It doesn't even need to be there. Okay, that doesn't need to go there. So we always look there. Okay, if we look again, so we know this, our height is negative 10. Okay, so we know this box here is going to be negative 10 meters. Okay, and then if I look at the total area altogether, if I look at the total area altogether, I'm going to do this over here, kind of like right there in that little box. If we look at the total area altogether, we're going to have 5 plus a negative 10. Let me put that in parentheses so we know it's negative. A negative 10. So if I add those together, 5 plus negative 10, it's going to be a negative 5, okay, because the 10 is more negative than the 5. So our total displacement is negative 5 meters. What that means is we moved 5 meters towards our original starting point. We moved 5 meters away from that starting point, and so in this case it would be like to our left maybe. That's one way we could define it. Again, directions are defined. So that's area under the curve.